Hey yo. So do y'all see this?
Yes, sir. We can. Or yes.
Cool.
Sorry,
Oh
Mr.
yeah.
Yes, sir.
Yeah, yeah.
Yes, sir. Nah. Yeah. So this is the midterm two, and I saw this problem and I was like, oh my lord, this looks like my final. um.
PTSD.
Yeah. Flashbacks, crying. Think I had like a double feedback op amp, and I was like, what do I even do? But yeah. So for this, have y'all ever seen this kind of problem before in your homework?
I think it actually was on
We
our
have
homework.
that's the exact same problem from the homework.
Wow. Okay, well then I'll just skip this one. Have y'all had this one?
I don't think we've had that exact one, but I feel like I've seen something similar. But I definitely appreciate going through that one.
No problem. Yeah, I'll like I think I'll go through one just in case because I have the solution to that. Number two, I have the solution to. I mean, I have the solutions to all of them. But have y'all seen number three?
We haven't touched on filters yet, so I don't think that'll be a tested.
Interesting, interesting. Okay.
Yeah, we haven't done anything with filters, and I assume biquad parameters are filters. So
Oh, okay, yeah. Did he send out documents for the what's it called? Like all the different types of op amps there are? Like
yes, potentially. Let me look.
because like it should be like these really long equations or whatever that like are input impedances from if you're given this particular configuration, then you put in this resistor and this capacitor and these values into this long equation, and it'll be based on either biquad or it'll be based on
I don't think we
all
have
these
anything
different
on
types of op
biquad.
amps.
I don't think
What?
we have anything related to biquad parameters, so I don't think we have that.
Okay, so then I'll go through one and two, and just in case, I'll also go through number three, like
Yeah.
for y'all's next exam or test.
What's it? He
Do,
said
do,
he
do,
was going to put for the 2-port systems. He wasn't going to put a circuit. He was just going to ask like things about forward bias and reverse bias, and basically topological questions.
Oh, okay. So like whenever like a table kind of thing, but like a very long table.
I'm not sure. He said it would like you'd ask questions like when is something symmetrical, when is it reciprocal, stuff like that.
Okay.
That's just what he said in class today. He didn't give like an example of it.
In that case, um, I'll go through. Do you think problem two would help going through?
Yes.
Okay. Then I'll go through number two. I'll go through number one, and then I'll go through number three.
Sounds good.
So let me pull this up.
do you mind if I ask you a quick question about something?
Yeah.
So I remember part of the thing he was asking, or he had mentioned earlier today when he was telling what could be on the exam. He mentioned something about the frequency or the maximum frequency of oscillation, and it's not an oscillator problem. It's related to the Mason's U function.
Mm-hmm.
Do you know when, like, what condition, like, of the U function makes it the maximum frequency of oscillation? I don't know if that question makes sense, but I've been trying to look it
The
up and I haven't been able
maximum
to find it.
frequency of oscillation, is that for an op amp?
Yes. It's for yeah, I'm pretty sure an op amp, yeah. Or it's just a two-port
Because
problem in
I know
general.
that what he drew for at least for problem one is he said that the frequency is equal to the change in voltage between these 2 points, between resistor one or between the negative and the positive,
Yes.
divided by the input voltage. And I'll have to draw it out.
No, it's fine.
Let me.
I can just listen whenever you go over it. It's fine.
Okay.
Thank you,
I'll
though.
go through it. Yeah, I'll go through it in the next problem. Hopefully that covers the question. Let me see if I can open just Paint. There we go. Okay. So then let me just cut the screen. There we go. And then let me expand this out if it'll let me. Oh, that's not what I meant to do. Maybe Paint is the way to go today. Maybe it's now calling my name because resizing is annoying in this one. Wait, no, it was right there, the resizing. I'm so sorry, y'all. There we go. That was weird. For some reason, that was just missing. Okay, so we got this problem. Two-port network, NA and NF, are combined with a series parallel interconnection, as shown in Figure 2. The hybrid H parameters for NA are given in matrix format below. If this connection does not violate port constraints for the two ports, calculate all possible realizable values for the resistors R1 and R2 such that the overall or total port NT has the following properties: unilateral in the forward direction, and the product of the diagonal H parameters elements is unity. Show your work and explain. So then for this problem, general things are starting with H. That is, oh, that's a very thin line. Let's go with the brush. Unfortunately, I do not have my pad that I can draw on here, and so now I have to use a mouse, but we'll see if we can make it through. So this parameter is equal to V1 over I1 when V1, or sorry, V2 is equal to 0. And then we have HF is equal to I2 over I1 given V2 is equal to 0. And we got two more parameters. We got HR F equals, we're going to do V1 over V2, and that is when I1 is equal to 0. Do y'all know if this is all in your materials? Like, do you know where to find this? Like,
Yes.
cool. I1 over I2 over V2. Given I1 is equal to 0. I really wonder how people come up with the derivations for these, because these two-port networks are pretty crazy, but they'd also be very helpful. So HI, this is starting for, this is the same circuit? Yes. So it starts off with this section right down here that says for this circuit, when V2, so when V2 equals 0, then we have R1 times R2, or you're going to have the two in parallel, is what's happening. Is that if the voltage is 0, then then this short circuits. Because this is, for instance, if 5 volts is on this line and 5 volts is on this line, then 5 minus 5 is 0. So you would be effectively short circuiting them, or yeah, you'd be short circuiting them. So that means we draw a line here, and then from that, this just turns into resistor in parallel with resistor, and that'll get you R1 and R2. And so then they're in parallel. So then it's just a R1 over R2, or R1 times R2 over R1 plus R2. And this makes sense because V1 over I1 is just really the impedance is Z1 whenever V2 is equal to 0. So that's why HI, or I guess the input impedance, is going to be R1 times R2 over R1 plus R2. So far, so good? Does that kind of make sense, or is it a bit confusing?
I'm good with it.
Is everyone else all right with it? Because I completely understand if that was a bit too over the top.
It was a bit. Could you try to explain it in more detail, please?
Yeah. Okay, so we have, let me scroll down here. We have this network. And so we are trying to find, we have these parameters for this top circuit. Like, this is a black box. We have zero clue what's in here. And so what we're wondering is what happens whenever we connect this circuit like this. Yeah, what happens if we just connect another circuit in this kind of parallel fashion with it? So what we need to do first is figure out, so let's explain. We have a black box up top, and then we have a circuit that we want to put in parallel with it. And we are wanting to know if whenever we do this, is it going to be unilateral? Wait, if this connection does not violate any port constraints, calculate all possible realizable values for the resistor R1. So we want to find R1 and R2 resistor values so that whenever you put these two circuits together, in T, so the total circuit is in unity. And it's also in the unilateral, oh my gosh, I cannot speak, unilateral in the forward direction. And the product of the two H parameters equals 1. So what we're doing first is we're taking this circuit down here and then asking what are its H parameters. And so what we've written is we have a matrix for HI, HF, HR, HO, and we're wondering, okay, then what are the value? How do we calculate HI, HF, HR, HO? And so then we have these equations that come along with it. And then what we do is for HI, we know that HI is looking for V1 over I1 given V2 equals 0. So what we essentially want to do is we take that circuit. We have this circuit where we have a resistor, R1, and then we have another resistor, R2, in this down here, we're taking that circuit, and we see that they cross each other. And so that looks pretty confusing, not gonna lie. And so that's like the question is how do we deal with that happening? And then we have the idea that there is a voltage here, V1, and then we have a current flowing this way called I1. And then over on the right side, we have a voltage called V2 with the current flowing into it called I2. So then at different points, we set V2 equal to 0. We set, just V2 and V2 equals 0. And then we set I1 equal to 0, and we set I1 equal to 0 again. And so what we do is we start with HI, where we say V2 is equal to 0. And so then the question is, okay, well then what does V1 over I1 look like? If we set V2 equal to 0, what does V2 equal to 0 look like? Well, whenever you have a line like this, you have this point and you have this point. You have a voltage on the top line and you have a voltage on the bottom line. Now, if I had 5 volts here, 5 volts, and then this has 5 volts down here. Whenever we say V2 is equal to 0, we are saying that this line and this line are the same voltage. Because V2 is equal to, if I were to call this VA, like node VA, and I call this node VB, V2 is just going to be VA minus VB. And since that's equal to 0, I feel like I'm making this more confusing than it needs to be. 1 second. I'm thinking of like a proper way that like
30.
No, I
how does
understand.
V2
Since-
equal
since
0
they're-
look like?
Yeah, since they're both the same voltage, there's no voltage drop, so it's effectively 0.
It's essentially a line that connects the two. Because this point's 5, this point's 5, 5, 5, 5, 5, all the way through is 5. And any point minus another point will end up being 0. So that's essentially what it's saying. Is that this whole line is 0 volts, which is a short circuit. So then I2, I'll draw a line here. And then what you'll notice is that so V1 over I1 is called Z input. So the input impedance. What that means is that if I were to redraw this circuit, you have R1, and then you have R2, and then like whenever you're walking around your home and you have just a ton of cords lying around, like we're just gonna rotate that wire or whatever, that cord, and so it's really just gonna look like that. That like this whole thing right here looks confusing, but we know it's all 0 volts, so we're just gonna unwind the cord. We're going to get rid of this like cross because this cross looks confusing. So we're just gonna draw it as a straight line because that's what it ends up being, is that it connects these two parts. And then this circuit right here. Let me explain ZN. ZN is the input impedance. So if I had a bunch of circuitry over here, no matter what it is, if it's a bunch of resistors, capacitors, inductors, whatever, ZN is just what if we were to condense all that to just a box, or like not a box, but like an impedance of some resistance plus whatever J value. So like if I had a capacitor here and I had an inductor here or something added here, pretty much I'm adding all of this together in whatever series parallel addition needs to be done, and I'm just essentially erasing all that. Let me see if I can like delete boxes. I'm essentially just erasing all that and then I'm condensing it all into just one box, saying that this is the input impedance and this is the resistance that you will see right here. And so that's the kind of idea for input impedance. That's kind of like why we care about HI, or where the I stands for input. But to clear up, I feel like I may have made things a bit more confusing than it needs to be. You'll learn more about input impedance in EMAG. But I mean, if you haven't already gone through that kind of stuff right now, or if you're not in that class already. But yeah, so we essentially V2 equals 0. So it makes this whole thing a resistor, and then straight line resistor, and then this can really just be looked at as resistor parallel with resistor, because these two resistors would be in parallel. So then you have R1 and R2, and you have plus minus V1, and you have I1 going this way. And so then you just add the resistors in parallel, which gets you R1 times R2 over R1 plus R2. Does that make a little bit more sense?
Yeah, it's good.
It's good? Okay. So then moving on to HF. So HF, let me kind of erase this part. What we have is a current divider. We have I2 over I1. We set V2 equal to 0. So it's the same circuit that this right here, whenever you set V2 equal to 0, you still get the resistor. And then this right here was technically RV2 plus minus minus and then resistor. This was technically how the circuit would have looked here. Actually, wait. Sorry. That's going to be negative back here, positive right here. Because following here, you would see that the positive would go in this way, and then it would lead down R2. So then that means positive is facing R2. And so since this is R2, this would be the correct way of drawing it. R1. And then you have plus minus V1 with I1 going this way. Now, with this circuit, you can see, does this look like any divider that you all know of? Would this be a voltage divider or a current divider? Like, let's say we're trying to find.
I mean, it can only be a current
That's why it's a
divider.
group
We
from,
got currents,
from
right?
the group, because I wanted to like venture out.
It said it could only be a current divider because we're dealing with currents, right?
Yes. Yeah. So oh, okay, I see how. So let me replace that with the voltage thing right here, minus plus. So we know this is V1 that provides a current I2. And you can see from here, we need to find I2. Well, just like I was saying with the current divider, I2 is just going to be what do you think the current divider here is going to be? If we're trying to find the current going through R2.
It's gonna be R1 over R1 plus R2.
Awesome. And then it's crazy that we just happen to multiply it by I1, because then what happens if we divide by I1?
We get H of F.
Exactly. I2 over I1 is just equal to R1 over R1 plus R2. Cool. And so then let me just, does that make sense to y'all why we got that?
Mostly.
Mostly. Are y'all confused about how we got to this part? Like, did that kind of make sense or no?
Not really. No, that's
Not
the
really.
bit that was confusing. After that,
Okay.
like it's easy to see what we're doing, but how we got there is.
So then I'm gonna try to go through this part again, this part right here, because that it's always gonna be those little things that like it's gonna be like, okay, you may know like the entire thing after that, but then if you didn't know how to derive that first part, then like you're just completely stuck. So I'll redo that. Let me do R2, or sorry, R1 over R1 plus R2. So then let me zoom in on this part down here. And let me get rid of this figure part. So we have a circuit here that, oh wait, let me also get rid of this line because this line wasn't here before. Cool. So we have this circuit right here where this is V1, and then the current I1 goes in here. So far, so good?
So far, so good.
Cool, cool. And then we have V2, which is right here, and I2 goes in here. So far, so good?
Gotcha.
Okay. So then this is really confusing. I think like the flip, like once you see that, then it's like, what's going on here? So the way I would explain this is that, let me redraw this as if like ignoring all of this other stuff outside. We have a circuit with V1 and I1 goes this way. And we have a resistor R1. Oh. And then we have another resistor R2. We have V2 plus, minus, and then we
I think
have
you have to
our
flip that.
I2 going this way. Do what?
I think you have to flip that.
Oh, cool, cool. So then from here, oh wait, I missed the flip. So this goes this way, and this jumps over this way, and then it's V2, and then I2 goes this way. Plus, minus, something like that. So what I would say is that we can replace, let me do delete this and write a voltage source. So we place a voltage source here, positive, minus, and we say that this voltage source, V2, is equal to 0 volts. What that means is that this entire line
Is a short circuit.
is 0 volts. And so that's where the short circuit term comes from, is that we placed some power supply that's producing 0 volts across here. So it's not adding anything to the system. It's just there. And if it's providing nothing to the system, it's just essentially just a wire connecting the two. And so because it's just, let me not erase it yet. If I, let me see if I can expand the borders down even more. There we go. So if I were to draw this down here, to deal with this is essentially making this guy is just flipping it. So now it's negative positive, right?
Right.
So then in that case, this circuit's going to look like V1, R1, R2. Gonna place R2 right there. And so if we flip this, we move this wire over here, and this wire then kind of moves down here, which essentially just makes a straight line. We just rotate it. We just rotate the wire. And so now we got that that weird like overlap out of the way. But rotating the wires like 180 degrees is just going to flip the power supply. So that's going to make this negative and this positive. And then that's our V2. And that means that I2 is headed this way. Does that kind of make sense so far?
Yeah, it makes total sense.
Okay. So then the question is, how do we know if R2 is in parallel or in series with R1? And the way that we can do that is by kind of rotating the circuit in like a way that like we can kind of better see whether it's in parallel. If we were to increase the length of this wire and we were to get rid of a bunch of length of this wire, essentially what would happen is we have R1 with our V1. And then if we get rid of like this much length of wire, then there's just going to be this much wire left. So that's just going to leave you like this much. And then you can draw your negative and plus. And let's say we shorten this wire, we shorten it down a little bit. So now we only have, say, this much wire, and we have our resistor. And then we increase the size of how much wiring we got here. We make it much bigger. And then now you see that you have V2 equals 0, and you have R2. And then that's how you get them in parallel. Does that make sense?
Yes.
Cool. So then from there, we have, we have our HI, HF, HR, and HO parameters. So we conclude that HI was adding in parallel. We concluded that HF was a current divider. Now we need to figure out V1 and V2 when I1 equals 0. So then what we can do is let's draw our circuit. Resistor, resistor. Oh wait, resistor, resistor. Oh wait, never mind. I would not draw a line there just yet. I'm going to leave it open because it'll be negative, positive, V2, because we haven't attached anything to it yet. Just like how whenever V1 how V1 was left open last time. Well, now since we're not attaching anything to V2 yet, we're going to leave this open for right now. Which maybe is completely wrong, but we're about to find out. I1 is set equal to 0, so we know I2 flows this way. And then I1 flows this way. So essentially, we connect it with a wire. And so if this is 0 current, if it's 0 current, does that mean that electrons are moving really fast across it, or like just not moving at all across it?
Not moving at all.
Not moving at all. Okay, so if electrons are not moving at all across it, would that mean that it has a really high impedance? Like if it's not moving across at all, would that be an open or a short?
Open.
I don't think we have to leave the world for that.
Open. So then I'm going to redraw this as resistor. Am I doing this right? I believe this so far is right. Yes. And then we have our V2, which I'm actually just going to see if I'm going to add a power source here. I think the idea is that you do add a power source each time, that both sides have a power source. So probably whenever I drew it like this was really a power source. So every time that you draw it, maybe you should draw a power source just to make things more clear. But just know that that power source isn't 0 and it's not infinity. It's just some voltage V1 that generates some current that flows through there. Because in the end, this is some power source is attached, and it is providing voltage across these lines. This wouldn't be open just because I left it open here. So whenever you draw it, make sure that you add a power source each time. So then in that case, I am going to draw the voltage source there, and I'll draw the resistor here. So we have R1, R2, and then we don't have these wires here because they don't lead off to anywhere, like super high impedance, nothing's flowing. That means it's just going to go through the regular resistors. So then from here, we are wanting to know, we look at this top one. Oh, where's my mouse? There it is. We look at this top one, we want V1. Well, okay, maybe I should have left the wires because because V1 is right here. V1 is the measure across this point and this point. Well, if we want the voltage at that point and that point, what does that look like? What kind of, is that a certain, is that like KVL or KCL or like voltage divider, current divider?
I believe it would be looking for the voltage, right?
Voltage divider. Okay. So then from there, we're going to say that V1 is equal to R1 over R1 plus R2. One second. Oh, yes, I see what went wrong. This is positive and this is minus. Current goes, since current goes this way, that means current's going this way. The convention is for resistors, for current going through a resistor, it's positive. Current goes in the positive side and leaves out the negative side for resistors. So then this convention here, since it's positive and then negative, or technically, what I'm trying to say is that there is going to be a negative sign. And so I'm trying to figure out the exact reason why it's a negative sign. And it is because of the passive convention of how you work with resistors. That current goes into the positive side of a resistor and comes out the negative side for the resistance to be positive. V1, V2 is supposed to be right here. But because be the best way. The best explanation I can give is that we know that this is facing down while this one is facing up. So if we had like a source here, goes in, resistor here, we had a resistor here, and then we had this positive minus. If we had this kind of thing, then this would have been positive. But we know because it did that cross thing that now it's really this way. And so from that, R1, R2, since we set I1 equal to 0, I realize that this is actually supposed to be a current source, but let me erase this part. Here, current goes this way, V1. Let's see, so this makes 2 loops. That's what I'm gonna say. I'm gonna say we're gonna have mesh 1 and mesh 2. You see, does that help? Yeah, I'm trying to think of like the smallest. Do y'all kind of get what I'm trying to go for? But like, you get why it would be kind of like confusing.
Yeah, yeah.
Yeah. What would be the best way that like you think of like you see it and it's like, oh, that makes sense that that would be negative. But really it's because of passive sign convention that current goes in positive, leaves out negative. So for power supply, for independent and dependent sources, current comes out the positive side. But because resistors take away that energy, current leaves the negative side. Or no, that's wrong to say. I can't say that current comes out the negative side. But whenever going through this, in order for the voltage of resistor 2 to be positive. Oh wait, maybe I can describe it like this. You have I2 goes in, I2 goes in this way, positive, negative. But then whenever it goes across here, because it's going in opposite direction that this thing is going, that this is going to be positive and that this is going to be negative, it is going to be negative. So if you ever see anything like this flipped, just know that if you do a voltage divider like this, be careful of the positive and minus signs because those can quickly make it negative. And that could like score you a few wrong points. So just watch out for the negative signs. That's about as best as I can say.
Okay.
So then for this, the final answer would be for HR. That's going to be your voltage divider of negative R1 over R1 plus R2. Because once you divide V1 by V2, that V2 that was right here cancels out. So then for this problem, or for HD, or HO, sorry, we have I2 over V2 and I1 equals 0. So then we're going to do current source goes this way, we know that its current is going to be 0 amps. And then it's going to go a resistor. We have this upside down voltage source going this way. Resistor, R1. And, oh, sorry, R2, sorry. R1. And we got V2. And I2 flows this way. So then from this, if we want to find I2, okay, I think I see how this goes. So there is no current flowing through this, right?
Right.
So we can pretty much get rid of it. And what this circuit ends up being is you have positive, negative for V2, flows into resistor R2.
I think it would be resistors in series, wouldn't it?
Yes, they would be in series. And then we have I2 flowing this way. And then if we're looking for I2, so how would you find I2 in this case? Like we
would
know
be,
that I2, yeah,
It would be V2 divided by R total.
V2 divided by R1 plus R2. And from our handy dandy notebook over here, we see, oh, sorry, that was like weird. We see that V2 is being divided out. So then that gets us I2 equals V2 divided by the sum of these, because it'll be V equals IR, so you just divide both sides by R. And since the total resistance is R1 plus R2, you just move it over, divide V2 by the resistance. And then now that you have I2 divided by V2 is equal to 1 over R1 plus R2. And then that is your 4 parameters. And then
Stop me if I'm wrong, but I think I see a pattern here between like the H in and the H out and the H forward and the H reverse.
Mm-hmm.
Yeah, see the H in is basically a parallel, right? And the H out is well, could you say it's not a parallel, it's like a inverse of a series.
It'd be the it seems to be a conductance. Is that I2 over V2? Because like usually impedance is V2 over I2, but then flipping it makes it like a conductance. HI is something that I probably care about because that is essentially saying you have this whole black box, and then you're wondering if I put a measuring multimeter right here or multimeter or whatever, what is essentially its just impedance? Like what Z value equals some resistance plus some inductance. That's the idea of input impedance. H forward and HR, I'm not exactly sure the exact reasons why we would use these, because it hasn't come up in my stuff yet, but it would more be whenever you're working with really complicated circuits, because you'll get to some like crazy circuits that you need to simplify down to just a few components for the simulator to understand. Um, and so that's why you would mainly do 2-port networks. But you'll probably not encounter that until like way later in like some kind of like Texas Instruments like kind of a problem. But in terms of like how do I look at this kind of problem, is that you look at the circuit that it gives you, or you look at well, of course, you look at the resistors and if they have capacitors there, all right. You look at the circuit that you do know, and from that circuit, you want to apply this number. You know that you have a voltage or current source on the left side, and you have a voltage or current source on the right side. And then your first thing to do is you set the voltage on either side equal to 0, or you set the current on either side equal to 0. Those are your first like 2 steps. Is take the circuit you do know and then apply voltage or current sources to both sides, and then set whatever value it says equal to 0. You just set that one equal to 0, and that will produce a open or a short. And then that will give you a circuit that you can then condense down or apply current divider or voltage divider or apply Ohm's law to, or KCL or KVL. One of those 5. Everything is either voltage divider, current divider, KCL, KVL, or Ohm's law. Those are the 5 most important laws. And then from there, you look at this number, the numerator. You look at the numerator and you decide, how do I get that number? How do I get V1 from the circuit I have now drawn? How do I get I2 from this new circuit that I've drawn? And once you find that value, more than likely the value that you're dividing by is just to cancel out some value that you got into I2. So then for HO, or sorry, yeah, we found HO, the I2 over V2, 1 over R1 plus R2. Just do y'all have any questions up to this point?
I'm good.
Okay. So then from here, now we can start using, now we can get to the actual math, y'all. Now we start using this guy. So what we want to do is HT, this H total, is equal to the H parameters of NA plus the H parameters of NF. So then whenever we add them, we get HT equals, up here we got 200. So we'll write 200 plus this first one, R1 times R2 over R1 plus R2. And then we have 80 plus R1 over R1 plus R2. And then we have our 0.2 in the top right. And then that is minus R1 over R1 plus R2. And then we have our bottom right is 50 micro. Plus 1 over R1 plus R2. So then from there, we have a question of calculate the following property of unilateral in the forward direction. And so this is going to be defined in your port definitions document. And unilateral in the forward direction is HRT. Uni in F equals H reverse, which is equal to 0.2 minus R1 or R1 plus R2 equals 0. And then we solve for this equation right here. And then that's just going to get us, we're going to bring this over, that's going to be negative 0.2. The negatives cancel out, so that's going to be R1 over R1 plus R2 equals 0.2. And then that's just going to be R1 equals 0.2 R1 plus 0.2 R2. And that just turns into 0.8 R1 equals 0.2 R2, meaning R2 is equal to 4 R1. You just move that over and divide it. So then that's going to be our first part. R2 equals 4 R1. And you can do it the other way too. It doesn't matter which direction you do it. Both answers are equal. Like you can do R2 over 4 as well. So that's R for unilateral in the forward direction. And then this connection does not violate port constraints. Calculate all possible realizable values for the resistors R1 and R2 such that the overall or total two-port NT has the following properties. So the reason why I'm taking a pause is because this does have it as the answer, but then he just did the extra step of let me circle more of this. He did an extra step. Actually, let me just delete it, honestly. If y'all are done with the work here, I'm gonna just delete this part. Actually, wait, no, I can just expand this document more. Even more space.
Infinite space.
Infinite space. Yes. So from here, move over. Oh, too far. All he did was that for the final step of it, he just substituted it into the H parameters. I don't know if this is required for the final answer. But that just turns into 200 plus 0.8 R1. And then this turns into 80.2. Why is it turning? Then it gives you 0 in the top right. Because, oh yeah, because of this relationship. That 0.2 minus R1 over R1 plus R2 equals 0. So then top right turns into 0. Bottom left probably simplifies somehow using that relationship. And then the bottom right turns into 50 microsiemens plus 0.2 over R1. So if y'all end up having extra time on the test, maybe write it like this. If y'all don't, I feel like this is acceptable. Because, I mean, it pretty much tells you HT. Does it?
Basically, since R2 is equal to 4R1, we replace the R2s with 4R1s and then simplify from there.
And the R1s cancel out.
Yeah, like if you go up and you go to the reverse corner, that's going to be R1 plus 4R1, which is going to be R5, which is going to be 5R1. So R1 divided by 5R1 is 1/5. So it's going to be 1/5 minus 1/5.
That makes sense. And then 80, that just simplifies into 0.2 as well. Or that you got this turned into 0.2. So then this is going to turn into 0.2 as well.
Right.
Yep. Cool. That's all. Or wait, no, sorry, that's not all. There's part 2 for the unity condition. And that's going to be for HI T times HO of T equals 1.
What does the T stand for?
What's what?
What does the T stand for?
The T stands for total. So it's it's this relationship right here. Oh, I almost tried drawing it. It's this one right here. That it's whenever you add up the H port conditions for this plus the H port connections for this one gives you HT.
Gotcha. And the bottom one is H N of F, right?
You think it'll make it?
Let's see.
Yes, because
Yes, so the bottom one's H and F. So then for this one, this is just, you take HI, and then you take HO, which is this one. You multiply them together, and then you get a relationship between the two. Which, whenever you do it, it'll get you a number of 40 times 10 to the negative 6 R1 squared plus 0.01 plus 16 or 0.16 minus 1 times R2 or sorry R1 plus 40. Do the R2s cancel out? Oh, okay, yeah. So this is required. This is required right here. And the reason why it's required is because then that gets rid of your R2s. So I'm actually going to select this and then move this down a little bit. It is required to do this. Because now that you have it substituted, you multiply this value times this value. (200) plus 0.8 R1 times 50 microseconds, or sorry, 50 microsiemens plus 0.2 over R1 equals 1. And then whenever you multiply that out, that comes down to let's see. There's plus 40 equals 0. And then where'd it go? You'll divide both sides, you'll divide everything by this number, and that divides out, and you add these together, and then you do a quadratic formula, and that'll get you an I'll get you R1 values of 48.305 and then 20.70169. I'll add the extra numbers for this one up here. So 9, and that is 48.30522 ohms. Which in here it says both are acceptable. From that, you go back to h of t and you plug in your R1 values. And now h of t equals 238.6442 ohms, 80.20, 4.190339 Siemens. And then let's see. And this is for reverse equals 0 for your unilateral forward direction. And then HIT times HOT equals 0. Then for part B, sorry, number 2. Wait, oh, I think that's, oh, 1 second. Oh, yeah, that's all. Yeah, that was part B. And then that should, let's see. He states that both solutions produce an amplifier that is unilateral in the forward direction and that has a product of HI and HO that is unity. And that notice that HF for both cases is the same at 80.2 amps per amp. And then that's all it says for problem 2. Does that kind of make sense for that problem?
I got kind of lost there at the end when we were calculating
fair.
the H total.
Do you want me, how far back do you want me to go?
I think you got to go soon.
Okay, so that's what I'll do. I'll just like run a little bit through it. Is that like if y'all kind of got the understanding for how to develop your H and F parameters, what you do is that H of t equals both of the H parameters combined. This one for your active network, and then this for the network you're adding.
Yeah, got that.
Once you add them together, you have your HI, your HO, your HR, and your H forward. You look for it'll state the which direction, or it'll state like this kind of statement, and you want to look for which property corresponds to unilateral in forward direction or unilateral in reverse direction or all those kinds of things. Once you find a value that corresponds to, it should state whether it's supposed to be equal to 0 or if it doesn't state it, then maybe it is supposed to be set equal to 0. But it'll give you some kind of statement. It'll give you some kind of equation. And then from that equation, it'll ask you to you'll just plug in those values and you'll get some relationship between those. And in this case, we got R2 is equal to 4R1. And because we got that relationship, that is now assuming unilateral and forward, that is a assumption that we make about our H parameters. And then we plug in that assumption that R2 equals 4R1 into our original matrix. And now it makes the math a lot easier for the next assumption that we're going to make. The next assumption is that, well, we want it to be in unity. Well, unity is whenever this parameter exists. So then what that does is, now that we have all the R2s gone because we plugged in R2 equals 4R1, and now we're just left with R1s. Now we just need to solve for R1 values.
With you
And
so far.
Oh, awesome, awesome. And so then we do a little bit of math. We like multiply everything out. We found because of quadratic formula, we got a polynomial R1 squared plus R1 plus some constant equals 0. We use quadratic formula, and that gives us R1 values. And so these R1 values say that for this op amp, that like this is supposed to be, this whole thing is diagramming an op amp or some active network that is using an op amp. And that what it's saying is that for these two values that we found, for these two resistances, from these two resistances, our op amp will exhibit the properties that we assume that our op amp will work in the unilateral and forward direction, and it will be at unity because of this property. And it'll work for the if we were to plug in our R1 right here, then we would get an R2 value, or we have a relationship R2 with R1, and then we plug in R2 into our total.
Hey, David,
It
go
then
down a little bit.
Yep.
I'm with you up until right there where it says H of T equals that matrix with the 238.
Yep.
And the diagonal, the 4.19 microsiemens. Those are what I don't understand how we got.
The way we got those is we took probably this value right here, first value, and we plugged into this equation here.
Okay, I see. So do we use the other one then, the 20?
It says both are acceptable. You can plug in either one, and it'll give you a matrix that either matrix will be accepted.
Okay. Now, will that be the case for whatever we find of R1?
Yes. If R1's negative, I'd be hesitant to use that value. So if you see a negative resistance value, maybe go with the other one.
All right, gotcha.
It's like a personal development.
But yeah, I have to head to class. I will finish problems 1 and 3. And then I'll like combine the videos together.
All right. Thank you. Appreciate your time.
No problem. You'll have a great one.
You too.